In the previous lesson, the transfer function was our zero-state map. Y of s equals x of s times h of s. Now we use that same map in a more practical way. Instead of asking for every possible time waveform, we ask how the circuit treats each sinusoidal frequency. The move is beautifully small. Take h of s and evaluate it on the imaginary axis by setting s equal to j omega. Frequency response is h of j omega. It is a complex number for every angular frequency omega. The magnitude tells us the gain at that frequency, and the angle tells us the phase shift. So the circuit becomes a frequency-by-frequency filter. Some frequencies pass almost unchanged, some are attenuated, and each one can be delayed or advanced in phase. Here is the key steady-state rule. If the input is A cosine omega t, then after transients die out, the output is A times the magnitude of h of j omega cosine of omega t plus the angle of h of j omega. The frequency stays the same. Only the amplitude and phase change. That is why frequency response is so powerful for sinusoidal analysis. Use the same RC low-pass transfer function from last time. H of s equals 1 over tau s plus 1, where tau equals RC. Frequency response means substitute s equals j omega. So h of j omega equals 1 over 1 plus j omega tau. At low frequency, omega tau is small, and the denominator is close to 1. At high frequency, omega tau is large and the output becomes small. From h of j omega equals 1 over 1 plus j omega tau, the magnitude is 1 over the square root of 1 plus omega tau squared. The phase is minus arctangent omega tau. At very low frequency, magnitude is almost 1 and phase is almost 0 degrees. At the corner, omega tau equals 1. The phase is minus 45 degrees. At very high frequency, phase approaches minus 90 degrees. Engineers usually plot amplitude ratios in decibels. For voltage or current amplitude ratios, dB equals 20 log base 10 of the magnitude ratio. A ratio of 1 is 0 dB. A ratio of 1 over square root of 2 is about minus 3 dB. A ratio of 0.1 is minus 20 dB, and a ratio of 10 is plus 20 dB. For power ratios, use 10 log base 10 instead. The Bode magnitude plot puts frequency on a log axis and gain in decibels. For the RC low pass, the corner frequency is omega c equals 1 over tau. At that corner, the gain is minus 3.01 dB. Before the corner, the curve is close to 0 dB. After the corner, it falls at about minus 20 dB per decade. 4 common traps. First, omega is angular frequency in radians per second. Ordinary frequency f is in hertz, and omega equals 2 pi f. Second, use 20 log for voltage or current amplitude ratios, but 10 log for power ratios. Third, phase signs matter. This RC low-pass lags, so its phase is negative. Fourth, frequency response describes sinusoidal steady state after transients have died out. Summary. Start from the transfer function h of s. Set s equal to j omega to get frequency response. The magnitude gives frequency-dependent gain, the angle gives phase shift, and decibels make wide ratio ranges easy to read. For the RC low pass, the corner is 1 over tau. The gain is minus 3 dB there, and beyond it, the magnitude falls at about minus 20 dB per decade. Next, we can compare low-pass and high-pass filters using the same language.